I'm Eric Hudson. I'm a professor at UCLA, and I want to welcome you to the Challenge Institute for Quantum Computation's Spring School on Quantum Error Correction. The Challenge Institute for Quantum Computation, or the CIQC, is an NSF Quantum Leap Challenge Institute that's specifically working to address the fundamental challenges to the development of the quantum computer. And part of that effort is to host an annual school on a topic of importance to the development of the quantum computer. These annual schools will be held in conjunction with the UCLA Center for Quantum Science and Engineering and the UCLA Institute for Pure and Applied Math. This year, the school was organized by Ben Reichart at USC, David Weld at UC Santa Barbara, and Norman Yao at UC Berkeley, along with myself. And when we met a few months ago to plan out this school, we realized this was quite an opportunity, because with the backing of the NSF and the CIQC, we hoped that we would be successful in going out to get the best of the best to come lecture to us on a topic of our choosing. And after some discussion, we sort of unanimously agreed that the first spring school should be on quantum error correction. Quantum error correction is clearly important to the development of the quantum computer, and it's moving at such a fast speed, it's difficult for those outside of the field to keep up with it. So we went out, we made a list of the top 5 people in the world that we would want to come teach us about quantum error correction. They all said yes, and we have the event before you today. I think this was probably a good choice because while we were building a school, anticipating maybe 25 to 50 attendees, at last check, the registration was about 500 of you. So thank you guys for showing interest and for tuning in. We greatly appreciate it. With that, let me also ask that you bear with us if there are any problems. While the lectures are world-class, the technology is new to us. We think we have it all sorted out, but if there are problems, please just click that help button. There should be live assistance for you quickly to get things back on track. I also want to take a moment to thank Carolyn Remick, who is the executive director of the CIQC, and Katie Christensen, who supports the UCLA Center for Quantum Science and Engineering. Both of these people put in an enormous amount of work, and without it, we wouldn't be here today. So if you see them in the chat rooms or maybe on GatherTown later, please don't hesitate to say thank you, because without them, none of us would be here. With that, let me turn now to the curriculum for the week. As you can see on the schedules, we have 5 lectures this week. The first will be given by Professor Jens Palsberg on classical error correction. This lecture is really to set the stage, provide the terminology, the definitions, and to give us a base for moving into quantum error correction. Tomorrow, Ken Brown from Duke University will give us exactly that, an intro into quantum error correction. This will be picked up on Wednesday by Austin Fowler from Google, who will delve into surface code. Then on Thursday, John Martinez from UC Santa Barbara will pick up the surface code idea, but then talk about how do you actually implement it in physical hardware. And then finally, on Friday, Shruti Puri from Yale will be telling us about work going beyond sort of the state of the art now, really looking at bosonic error correction, which is an idea that she's been developing. And now let me introduce today's lecturer, Jens Palsberg. Jens is a professor of computer science here at UCLA. His research interests span programming languages, software engineering, and quantum computation. He's a member of the ACM Executive Committee, the ACM. He's the chair of the ACM SIG Plan, and he won the ACM SIG Plan Distinguished Service Award in 2012. Jens is also a friend of mine, so I can provide a little more information about him than you'll find on his CV. Jens used to be the chair of the computer science department here, and during that process, he got interested in how exactly are you supposed to run an organization? And he decided to go back to school and get an MBA. And he wrote a really entertaining blog about it titled, "A Computer Science Professor Wants an MBA." I encourage you to check it out on his website. Don't do it during the lectures, but maybe on your leisure time. I think you'll find it entertaining, especially the part where they made him take a test to make sure he knew enough math to get an MBA. So with that, I'll hand it over to the capable hands of Jens. Thank you, Jens. And all of us, let's welcome Jens.
Also, we compute and we communicate. but our devices and our communication channels are imperfect, and they corrupt our data. And the question is, how do we detect and correct the errors? And I have a lecture for you today where I have a single purpose. The purpose is to persuade you that classical error correction, a lot of classical error correction is applied linear algebra. And I welcome you to ask as many questions as you like. We have the whole slot from now until about 3 hours from now, and you can ask me as much as you like. The way it's going to work is ask questions in Q&A. It's better to use Q&A than to use chat. And we have a moderator today, August Hirth, who is a PhD student at UCLA and an experienced moderator. And what he will do is that he will, first of all, read your questions, and sometimes he will answer them, and other times he will then, when there's a pause for questions, he will read them aloud. And I'm going to pause for questions many times, and I will be very happy to answer questions, as many as you have. And so the goal is to persuade you that classical error correction is applied linear algebra. And I will go into 3 points to support that. First, I will introduce the idea of classical error correction. I will talk about the early history. And then second, I will show how encoding and detection of errors can be done by linear functions. And so that's the linear in linear algebra there. And then I will go into details of the reason why linear codes will work well. And so you can see I have 3 main points I want to go through, and I'm planning to take a tea break once or twice during the day. And what I will do is that I will open up my iPad, and then I will scribble on the iPad simply to slow myself down so that you have time to think and have time to realize what your questions are and ask. And I just want to repeat the same thing as my primary school teacher said all the way back then, which is that it's the smart people who ask. So please, there's no such thing as a stupid question. All questions are good, and we will answer all the questions. So please ask. Okay, so let me begin with my first point. So what is an error, and why can we hope to correct it? So that's the beginning. And so we're going to get into the idea of error correction and the history of error correction. And so let's just start with something major here. Classical error correction means that we are working with classical data. And so it means that we are working with bits, and an error means a bit flip. And of course, a bit is really either a 0 or a 1. So this means that a bit flip is flipping a 0 to a 1 or flipping a 1 to a 0. And so that's really what we're dealing with. And just to have some notation, I'm going to use capital B as my set of bits. It'll be nice to have some notation for that as we go along. So there it is. So then we can ask, okay, so how often do bits actually flip? And so just to give an example, let's look at an Intel computer. So an Intel computer that I used to work with, which is one of the Intel Xeon computers. So how often does it experience a bit flip? So I'm thinking about a particular Intel Xeon called the Phi processor. Some people call
Professor, you've frozen, it seems.
it the night corner, and very so it has. But thanks for telling me. Can you see that
You are cutting out intermittently.
Oh, that's not good. But thanks for telling me.
Yeah, it seems steady now. Let's see how it goes.
Yeah, so we have a case of classical error on the communication line, just to illustrate the whole point. But I wanted to take my example from a computer instead of from a communication line. So let me return to this Intel. So what is it that can happen in a computer? So of course, the computer is full of bits, representations of bits. But what can happen is an alpha particle can hit the computer, can hit the storage, and a bit can flip. And so how often does that happen? And so this error rate there is what normally is called a soft error rate. And so the error rate is what we can find on the web page for that computer is something like one error every 1,000 years. So let's just write it that way. One error every 1,000 years. That's really low. But we still use error correction just in case. You never know. It would be sad if it's exactly the day we get an error. So we do error correction. Now let's contrast this just for a moment with a quantum computer, just to see what the error rate is. So let's take an IBM Q16. Some people call it the Rushley-Con quantum computer. Very nice quantum computer. And I looked up the data for error rates from 2018. And so it has some different error rates. I just want to give you a sense. I think it's fairly representative of the field. So if we look at single qubit operation, we are talking about error rates of, let's call it 2 errors per 1,000 operations, not 1,000 years, 2 errors per 1,000 operation. That's a lot, that's orders of magnitude more errors than on the Intel Xeon. But we should, of course, also look at 2 qubit operations. Very important. Higher error rate. Now we are up to 44 errors per 1,000 operations. And then, of course, quantum computers also need to do measurement. So just to sort of complete the picture here, measurement. So now we are up to 60 errors per 1,000 operations. So just to say that error rates can be very different. Of course, we can talk about error rates in other places like communication, like we just had before with the error on the communication line between me and you. But the point is that error rates can be very different, and especially in quantum computing, the error rates can be pretty high. So it's very clear that if we need error correction in classical computing, we need error correction even more in quantum computing. And so the question then is, what do we do? And so there's a very simple answer, which is add redundancy. So this is the key to everything. Add redundancy such that when we, for example, send data or store data and an error happens, then because of the redundancy, we can recover the data. And so if you like, we can take in the spirit of the pandemic, we can say that we want to immunize our data. And so in this case, we want to immunize our data against noise. And really what we want is that after we have added redundancy to the data, it's better to send the immunized data than it is to send the raw data. That's where we want to get. So whatever it is we're going to do, we want it to be better to set up for error correction. And so that's where we're going. So I'm now going to talk about some sort of basic considerations, but at the end, when we are way later today, we will talk about, is it really true that adding redundancy will make it better to send the immunized data than it is to send the raw data? So let's take an example. So let's say that I'm going to send email to somebody, or maybe you are going to send email to somebody. And what we'll do in this email is that we will say, I'm willing to lend you $100. However, there is a possible error, and it's a very funky error. That error has a tendency to sometimes replace exactly the part of the email that says $100 and change it into $1 million. And sometimes if you write $1 million, it might change it to $100. That's the only thing. So it's almost like a bit flip. I'm sort of making this up a little bit. So you don't really want to be on the hook for lending out $1 million, and I don't want to be on the hook for lending out $1 million. So the question is, how are we going to go about this? Are we going to just send the email that promises to lend out $100 and hope the best? Or maybe what we could do is that we could consider to send the email twice. So how about we send the email twice, and then we tell the receiver that if the two emails you get say something different, the one email says, I'll lend you $100, and the other one says, I'll lend you $1 million, then don't believe any of that. Ask me to resend the email. That would be nice. Then we would be detecting that then the person on the receiving end will detect that something is wrong, and then ask for a resend. Or maybe we should go even further. Maybe we should send the email 3 times. How about that? We send it 3 times, and then we tell the person on the receiving end that read the 3 emails, and then see if they all say the same thing, then it's fine. You can believe that. But if they're different, then 2 of them will say the same thing, and then you should believe that one. So that's sort of some ideas for what one could do. And what we really want here is that, especially the one about sending the email 3 times, where the person on the receiving end can work out for themselves what's going on. We want that to be better than just sending the single email of promising to lend out $100, and then maybe the communication channel will get it wrong. So the question is, how do we take this idea a little further? So now at least we have an idea of how we can add redundancy. And so what we are doing here clearly is we're kind of spreading out this information of $100 into 2 emails or 3 emails, and what we're really doing is that we are replicating the data. So let's just get that down. We are replicating the data, and in this case, the crucial piece of the data. And what we can see is that if we are replicating twice, so this means that we look at copying every bit from 1 copy to 2 copies, then we get a scheme like this. And what we can see is that in this case, we can detect that something went wrong. The person receiving it can detect that something went wrong. And so we don't know what went wrong, because in the case of an error, what we really get is that 0 gets transmitted as either 0, 1 or 1, 0, and 1 gets transmitted to, well, 0, 1 or 1, 0. So it means that if all we see is a 0, 1 or a 1, 0, we know something is wrong, but we have no idea what the original thing was. And that's exactly like if the person sees 2 emails, one promises $100 and the other promises $1 million. We don't know what was originally promised, but we know something is wrong. And so this scheme here is very much like talking on the phone, also, where sort of noise comes in, or as August said a minute ago, you're cutting out. Can you please repeat? That's exactly what this code is doing. And one thing that one should note is that this error here is a single bit error. And so that's working well, we can detect. But of course, we should also recognize that the error could be worse. The error could be on both bits. And if that's the case, then of course, now it's really bad. Now it's like we might get that when we transmit, we get 1, 1, or we get 0, 0. And in that case, it looks like a totally legitimate thing. And we have no idea that an error even happened. So that would be bad. That would correspond to that we sent the email twice and both emails promises $1 million. Then that's terrible. So so what we're trying to do here is focus on the important case. And so what we are actually focusing on today, single bit errors are extremely rare, and then we just don't bother with the 2-bit errors. But then, of course, sometimes 2-bit errors can happen, and then we need to do more. But so what I will do is that for the longest time today, I will talk about correcting single-bit errors, and then towards the end, we will look at what needs to be done if we need to correct more than single-bit errors. So, but just to recognize that 2-bit errors in this case can be terrifying. So it means that we have the following scheme. So let's just draw a little picture here. So so I want to set up for for distinguishing between error detection and error correction. And so let's just sort of draw it this way. We have the sender over here. We have the receiver over here. Some kind of nice blobs around them. And with error detection, what we do is that we send data. So data goes that way. And then every once in a while, there's a request to repeat that goes this way. So it's like something comes across that's just not right. And of course, in the case of using the 2 bits from before, we can think of it as we look at the parity of what we receive. If the parity is 0, then we think we're good. And if the parity is 1, so that means sort of the sum of the bits is 1, then we issue a repeat request. And this should now be seen as a sort of a simple version of what we're getting to when we repeat 3 times, for example. Then we have the sender and the receiver. In this case here, we're certainly sending data from the sender to the receiver. But in this case, what we now hope to do is to correct. So I'm going to sort of draw the arrow that way. The receiver will not involve the sender at all. The receiver will look at the data, correct a single, that's what we've been talking about, a single bit error, for example, or if it's a more advanced code, we correct more errors. And then on the receiver, sort of on his or her own accord, will figure out what's going on. And so in many ways, we can think of that what's going on here is, in the spirit of the pandemic, we're giving the data a single shot. We want to give it a single shot so that the receiver can correct the data over here. So that's the thing. And so it means that if the data has gotten the single shot, it's ready to travel all over the world and be totally fine. Okay, any questions?
Yes. How do we make copies of the information we want to send?
So in a classical computer, we can copy as much as we like. So that's one of the lovely things about classical computers, is that copying is easy. And so it's for example, for the purpose of sending an email twice, it's very easy to go to the folder of sent emails and then send it again. Or of course, at the level of the machine level of a computer, there are copy instructions, and so it's easy to do. Very different for quantum computing, but for classical computing, piece of cake.
Can you clarify that in the quantum situation, what are the things that are causing error here? Are we sending or receiving, or where's the error showing up?
So in quantum computing, errors come from at least fundamentally that today's quantum computers operate very near the absolute 0. So very, very much like no more than 0.1 Kelvin is the temperature at which the quantum computers operate. And so it means that we are working in a situation where the atoms are pretty much lying still as we can get them. And it doesn't take much before this stuff starts to move around. It's like the outside world is just always trying to increase the entropy. And once the atoms start to move too much, the quantumness of sort of that we need for doing computation goes away. And so so at a fundamental level, it's like nature is just out to get us with the quantum computer. But of course, there are many problems. So for example, if you are using a laser to control your qubits, then it doesn't take much of a little calibration error or directing it a little bit the wrong way before something will not go quite right. And so errors can creep in for many different reasons. And given that we are in the later days of classical computing and the early days of quantum computing, people have had much more time to get it right in classical computing. But if you go back to the late 1940s or early 1950s, classical computing was full of errors in those days too. And so if we look at the error rates in those days, they would be much more like the error rates we see in quantum computing today.
Is there an equivalent type of error correction or an equivalent type of error for the decoherence error in the classical context?
I don't think so. So now we are actually asking a question here that is somewhat beyond my knowledge, because it's more of a hardware question. But I must say that I find these decoherence errors to be sort of really unique. We don't do classical computing at the level of 0.1 Kelvin or anything like that. So I want to believe that these decoherence errors are unique to quantum computing. That makes me feel good.
How do we distinguish systemic error versus random error?
I think that the best for today's lecture is to think of all the errors as random errors. But there is a consideration here, which is that if there's a systemic error of some kind, it could be that that this whole thing of saying, let's just look at a single bit error and not worry about 2-qubit errors, that this is just a fundamentally bad assumption. If there's a systemic error that at some point will just start to make every bit that comes along flip, then trying to correct for a single bit error is not going to be good. That's as we analyzed before, that's not going to take us very far. But there's a whole story about bursty errors that maybe could come from systemic errors that that people have studied, and I'm going to happily leave that out of discussion today. But people have studied it. But for today, I will simply think of the errors as random errors.
If we copied a bit only twice, will we be limited only to error detection and not correction?
Yes, very well said. That is indeed true, and we will return to that point. So that is exactly the thing, that that when it comes down to it, there is a difference between how things work with detection and correction, and in a way, one can say we need more bits. We need to add more bits when we do the encoding to get to correction.
For repetition code, if we can denote phase error by the Z gate and bit flip by the X gate, how good is the assumption of collective dephasing?
So this question, I know the answer, but I actually want to defer that question to Ken Brown tomorrow, who is the master of linear code for quantum computing, and I want to focus on classical computing today. So if you don't, after the lecture, I will be happy to go and answer as many questions as you like about quantum error correction ahead of Ken tomorrow. But for now, please let me stay on task here.
And I think the final question so far is, oh, it just disappeared, excuse me. What's the most common and the rarest errors that occur in the quantum setting?
I do not know the answer. This answer you will get from Ken. So please, this is, I want to hear that answer tomorrow too. So Ken knows the answer and he will tell you. Okay, so with that, let me move on a little bit. So I now want to be serious about repeating 3 times so that we can get into some error correction, not just error detection. So this is our idea. So we're going to do the following encoding here, and let's look at what an error can look like. So let's do again single bit flip, and so this means that we are looking at something like we're going to get something like maybe no bits have flipped, but if we see a single one, could be in, of course, 1 out of 3 different positions, then what we will do when let's call it, what should we call this? We could call it decoding. So if we see this we will do a correction to 1, 1, 1, and then to a 0, 0, 0, and we'll conclude that what was sent was a 0. And similarly, just to take all the other bit patterns, there should be 8 of them. Okay, so that was not quite what I meant to say. Yeah, I think we can do it this way. I think I'm writing the bit patterns in a rather random order, but that's how they came to mind. If we see either 1, 1, 1, or we see just a single 0 in there, then we should conclude that this is a 1. And we conclude that based on majority voting. So really, just look at the bits, see who's in majority, and that was the bit that the sender had in mind. So now let's look at this scheme a little bit more. And now comes something that will be important both later today, and it will be important for Ken Brown tomorrow, which is just like we said when we were transmitting 2 copies, that we can think of what the receiver is doing as checking parity, of saying if you receive 2 zeros or 2 1s, we'll say the parity is 0. If you receive a single 0 and a single 1, we will, in either order, we will say that the parity is 1. And so really what we're doing is that we're checking the parity. And what I want to ask now is there a way we can understand this story here as checking parities in the same way? So I said majority voting, that's fine. But now I want to think of this in terms of parities. So I'm going to organize this picture here in a different way. So what I will do is that I will say, we have a code word. So you know the data was encoded as a code word by taking 3 copies. And let me organize it in the following way. So first we have the good ones. They are here. Then we have the following tool. So you can see something happened with the first bit. Then we have this one. And again, if we're doing single bit flips here, then something happened to the second bit. And of course, then we also have that something could happen to the third bit. So I'm going to group the 8 bit patterns this way. And then I will introduce a term that we will use a lot today, which is the error syndrome. And so what the error syndrome is doing is that it's looking at 2 bits at a time. In this case, error syndrome is a general term, but I'm introducing it here to sort of give an example of what it can look like for this code. And so what we will do is that we will look at the first and the second bit together. So actually, maybe I should circle them down here. So let's look at these 2 together, first and the second bit. What can we say about the parity of these 2? Well, so they're both 0. So let me write that down over here. So we have parity 0. We can look at this one. What's the parity? It is 1. Okay, so we write this down. And we can go on. So in this case here, the parity is also 1. And then finally down here, when we get to the last case, we can see that the parity is again 0. Okay, so that's what we got. The idea now is that instead of just looking at parity like one time, we'll do it twice. And so I'm now going to do parity a second time. I will say, let's look at the parity of the second and the third bit that were received. What do we get? We get that the error syndrome in this case is 0. Okay, then let's do it again. So let's look at the parity of these 2, and we can see the parity is 1. It's 0. Hey, it's 0. Okay, 0. Okay, so after that one, we move on here, and we see the parity is 1. And then finally, the last one, we get that the parity is 1. Okay, so this is great because when we focus on combining into a pair of these parity checks, we get 4 different cases. And so why is this good? It's because we can now make a correct conclusion. Let me write the conclusion down just to make it absolutely blindingly obvious where I'm going with this. So over here, we have our conclusion is there was no error because we are working with single bit flips. All the bits were the same. So when we look up here, it's clear that a zero was transmitted. So we can conclude that. In the second one, we know that when we were focusing on our second case here, this is where something went wrong with the first bit. The first bit was flipped. So we're going to write that down as our conclusion, bit 1 flipped. And then similarly for the other cases, if we look at this one, we can see that that's the one where the second bit flipped. So I will write that as bit 2 flipped. And we know that the third one is that bit 3 flipped. So what we achieved here is that by focusing on 2 parity checks, we could get a lot done. We could actually work out, just by looking at the result of these 2 parity checks, we could see either that no error happened or exactly which error happened, which means that we can then go ahead and flip the bit back if that's what it takes. So that's sort of the idea. And I want to just give you a little bit of the early history of when that idea came up. So if we go back to, so in many ways, the key year here is 1948. So everything goes back to 1948, and that was Shannon. So Shannon started to write about the mathematics of communicating, and the whole field of electrical engineering and computer science owes lots and lots to that. So 1948, and then immediately people started to then work on error correction, classical error correction. And I just want to cover the first like 10 years of error correction, just to give a sense of how much was done and how much of it is relevant today to quantum error correction. So let me just throw out a few years here. 1949. That was GOLAG, turned out to be very good. When Voyager 1 and Voyager 2 were visiting Jupiter and Saturn, 79, 1980, 1981, thereabouts, they used GOLAG codes for the communication. So one of the very first ideas that came up for doing classical error correction was used in a big way. Let me throw out some other years. 1950, so we're still back there. That was when the first paper by Hamming came out. So again, one of the big names in classical error correction. So we got Hamming codes. And then the story continues. 1954, very famous Reed-Muller codes. And we can continue with, again, I just want to mention some of the really big ones that had a lot of impact on the field. 1955, we got convolutional codes. And so I am sort of bringing up all these things because in a moment I want to talk about which ones are a really good fit for quantum error correction and which ones are maybe best for just staying with the classical error correction. But let's do some other ones. So we have cyclic codes. It just keeps going. It's the thing is that these ideas are very different. Every time something comes up, there's a really new idea in there. So we got to cyclic codes in 1957. Then in 1959, we got BCH codes. BCH is actually, that's the abbreviation everybody uses, but it's actually named after Bose, Chowdhury, and Hockenham. But that's too long to say, so people say BCH codes. And then I'm going to end this story with 1960 when we got Reed-Solomon codes. The reason I'm so fond of mentioning Reed-Muller and Reed-Solomon is that it's kind of connected to Los Angeles a little bit. So I want to bring these up. So just to hammer home the point here that many ideas for doing classical error correction came up quickly, and people didn't stop in 1960. There's still new codes coming out. And of course, then what people started to do for quantum error correction is to say, which one of these would be a good fit to sort of bring over to the quantum side in some. this stuff here has been used. I mentioned Voyager was using Golang codes. We're using classical error correction for all kind of stuff. Of course, we talked about parity checks, which is used for storing on memory chips in classical computing. Of course, we use error correction in networks. This is where these cyclic codes are very popular. Then there's for digital circuits where really bits are encoded as sort of electric voltages. And we have to look at the noise margins there. There's again error correction. And then for satellite communication, Reed-Solomon codes are very popular there. But then there's this question of how should we look at these with the glasses of quantum computing and errors in quantum computing. And so this is where we have to sort of put on the glasses of what is quantum computing really. And so I'm going to sort of take the perspective that quantum computing is, I call it, applied linear algebra. So this is how I will see it. For the purpose of thinking about this, I will simply say quantum computing is applied linear algebra. And so what does that mean? It means that the codes on the left that use linear algebra, use linear functions in an essential way, they will be a particularly good fit for quantum computing, for quantum error correction. And so as it happens, there is a whole concept of linear codes. And spelled correctly, we can circle the linear codes in this here. And it turns out that there are quite a few of them. So Golang code is a linear code. So it means that it uses a linear function for encoding, and it uses a linear function for detection. And we can keep going. Hamming code is a linear code. As it happens, Reed-Muller code is another one. Cyclic code is another example, and Reed-Solomon code is another one. Okay, so there are other ideas in classical error correction than linear codes, other ideas than using linear functions for encoding and detection. But there are plenty of linear codes. And for just about all of these, the quantum error correction people have then sort of picked up and said, let's see what we can do. And let's see if we can use these ideas for quantum. And so what I will do today is that I will talk about how people make it work for classical. And then you will see Ken Brown develop the story tomorrow for quantum. Any questions?
In the classical setting, why do we need to look at parity as opposed to just using majority voting?
So the thing is that for this is a super central question. So I think the idea is that to get going on codes, we start with this thing of majority coding, but it's also wasteful. Every time we encode a bit, now we suddenly need 3 bits instead. And so in many ways, the whole goal of the field of classical error correction is to do better than duplicating everything into 3 copies. And so it means that we need a more general concept than majority voting. And so we can sort of frame the entire field of classical error correction, all of these codes that's on the page here, and many more after them, as wanting to transmit less than a factor of 3x what you want to transmit, and therefore generalizing the concept of majority voting. And the way to generalize majority voting is to get into parity checks. We need to do a little bit more general than just talking about parity checks of a couple of bits, but that's the idea. So we need to generalize these concepts. And in the end, towards the end, when I start to branch out and talk about more than just duplicating 3 times, we can see how much better people do in practice.
Can you elaborate on what an error syndrome is?
Yes, I will in many ways be elaborating on the error syndrome the rest of today. But let me now that I have my slides here, let me say that the error syndrome is a sign of an error, or maybe the sign of the absence of an error. So, so what we do is that we look at what we received, and then we do some, let's call it maybe I should not use measurement, but we do a little bit of sort of looking at it, and we see what we get. If our little computation gives us 2 zeros, we will say there was no error, but maybe we get something else. So, so an error syndrome is the word people like to use as look at what you received, see what you think about it, and make a conclusion.
What about more advanced codes like LDPC?
So they came later. So those codes showed up after, I think that's the 70s, if I remember correctly. When I took classical error correction as an undergraduate student, we had those codes. I took that after they were developed. I actually don't remember whether they are linear codes. That's a question that we can find out. But it is true that people kept working on linear codes way after the 60s. So they stayed popular.
Is the surface code an analog to any of the codes listed here?
Yes, these surface codes are linear codes. And so this is an excellent question. So you can see in many ways the design of the week here is that today I'm going to talk about classical error correction, and I will immediately say, let's focus on the linear codes. And the reason is that tomorrow, when Ken Brown starts to speak, he will say, let's see what we can do with linear codes for quantum. And then the practical way of doing something with linear codes for quantum is then to get into surface codes. Or maybe I should say, one of the most popular ways of doing something practical with linear codes. So, so I'm just simply setting up for all the big guns this week to talk about linear codes, and particularly as a special case of that, surface codes.
Can you elaborate on what you exactly mean by linear codes? What is linear here?
So yes. So again, this is I will elaborate on that the rest of today, but let's hammer it out here. So we are talking about linear encoding. So that means a linear function for encoding and a linear function for detection. So where detection means go and do some parity checks or generalized parity checks and see what you think about it. So this means from now on today, as soon as we are done discussing this stuff here, it's going to be all linear functions from now on. Whenever that we're going to talk about encoding and detection, it's going to be linear functions. So maybe I should simply say we mean, let me write it this way, linear functions. Other questions?
Why aren't BCH codes considered linear in this case, since they're cyclic?
So I looked at this and I cannot make them fit into linear codes. So maybe there's a way to understand BCH codes as linear codes, but I couldn't. It could be that I'm too rusty on BCH codes, and there's a way to think of them as linear. That's a really excellent question, and I wish they were, because the more of the classical codes that are linear, the better I feel for this lecture here. So let's hope we can get that settled. So I'm going to take that down as a question I should remember, and hopefully we can come back to it.
You mentioned that computers originally had very high error rates. Is the main reason that their error rates are so low now due to improved hardware or to error correction codes?
It is mainly due to improved hardware. So of course, hardware has changed tremendously over the years. When we go back to the late 40s and early 50s and the first decade of classical computing, that was before we had found out how to build transistors in silicon. And instead they had these tubes and they would break. Everything was sort of much more physical in a way, in my view, that you could sort of walk up to a computer and sort of break it very easily. But the hardware has gotten much better, and so that is the key to why the error correction rate is lower.
Do you ever deliberately perform bit flips to elicit some particular sort of result?
I do not have an answer to this question. I think of errors as something that should be avoided or managed, and so doing something deliberate, I don't have an opinion about. Today I'm totally in the mode of that errors happen, and when they happen, we deal with them.
Is it the linearity of quantum mechanics that limits us to only use linear error codes?
For quantum computing, yes, this is how I see it. So I wouldn't rule out that there could be some other ideas that could come in, but I would say short answer, yes. I want to see it this way. Quantum computing is sort of all linear algebra, and a good big chunk of classical error correction is linear algebra. So let the two meet, and they will meet tomorrow.
Can you do another very short example of a parity check?
I would like to defer this question to when I get into sort of generalizing this whole scheme as we get into linear functions for encoding and detection coming up soon. So yes, I do want to answer this, and I have a lot to say about it. And if I don't say enough, then ask again.
I'm going to fuse two questions here. The first of which is it fundamentally impossible to perform nonlinear quantum error correction? Is that just sort of how nature works, so we have to work with it in the linear code manner? Or is this a choice that we make to make things easier?
Okay, so I think this is a really excellent and fundamental question. The way I think about the answer is that if we are going to do the error detection and error correction on the quantum computer, the answer is yes, that it's a limitation of quantum mechanics that we have to do it in a linear way. And then I think we are, in practice, restricted to linear codes. However, one could imagine that the quantum error correction is done with some kind of interplay between a quantum computer and a classical computer, in which case the classical computer can, of course, as we have it here on this page, can do a lot more than linear codes, perhaps. And I think that this is where a fundamental question of this kind really should be asked also of the speakers coming later this week, who are like the best people we have on this topic.
Excuse me. By the linearity of quantum mechanics, are you referring to the unitary transformation or Schrödinger equation?
I am talking about the unitary transformations. That all work in quantum computing is done by unitary transformation. And so that's linear, and so that means that's the restriction right there. But to give a longer answer, I see this thing about the unitary transformation as almost like a corollary of quantum mechanics. That's just what we can do. This is what quantum mechanics allows us to do, and so okay, so we are restricted that way. And what the entire field of quantum computing is all about is to show that we can get a lot done with unitary transformations.
I think the last question is this one. Is the CRC related to the cyclic codes?
Yes, it is. CRC stands for cyclic redundancy check. And that is a cyclic code. Yes. So I was just, trying to be brief in my way of writing it down. So yes, very much so. Okay, everybody, let's have a tea break, and we'll come back to linear functions after the break. So let's just have 10 minutes of break to warm up and drink some tea, and come back something like 8 minutes after the hour, and then we'll pick it up then. means that as far as linear codes go, we can get BCH code in there too. So most codes, all the classical work, most of it is really linear codes. And so that's great. So it means that the quantum error correction people have a lot to sink their teeth into. I want to sort of make a point here about single bit flips before we get to all the linear algebra. Just want to make sure that we have down that if we encode a 0 as 3 zeros, then okay, so we can say that this is our encoding, and then some kind of error happens. So let's say we flip some bits, maybe not just one bit, maybe we flip 2 bits. So this means that if we get 2 bits flipped from zeros to ones, so that would be our error here. Then, of course, once we then on the other side do correction and we say, what should we conclude from this? And we are set up to do majority voting, we would correct this to 1, 1, 1. And then when we then decode, we are going to conclude that that was a 1. And so we get the wrong conclusion. So that can happen. So 2-bit flips is not going to be good for this basic copy 3 times and do a majority voting scheme. And of course, if we were to do 3-bit flips, then it's even worse. Now we get from a good code word to another good code word, and we don't even know that an error has happened. And so what we are after here is that we want to correct the most probable errors. And so the idea is that a single bit flip happens with some probability, and then we are going to assume a little bit like the discussion we had previously, that 2-bit flips that are close to each other are very, very unlikely, much more unlikely than a single bit flip. And so this is the justification here for why we are focusing on single bit flips for a lot of the discussion today. I see that there are a lot of questions, so maybe we should start with some questions, and then I will get into to linear encoding straight after that. So, but August, please, let's hear some questions.
Absolutely. Do you think error correction or hardware improvement is going to save quantum computing? Like it did,
I think that okay. So personally, I think that in the short term, by the short term means this decade, so up till 2030, I think it's going to be 2/3 hardware improvements and 1/3 error correction. I think that we simply must knock off some more error from the hardware to really have a realistic chance with the error correction. And so the reason is that the more likely the errors are, the more likely that you will get errors close together. And then that makes error correction really hard, as we are discussing here. We need both. We absolutely need both. We need the hardware people to improve the hardware, and we need the error correction people to come up with better error correction schemes.
Which of those linear codes is the most data efficient?
That is an excellent question. I will defer this question until later, but it's very clear that we want to do better than copy 3 times. As it happened, if we look at an earlier spacecraft than Voyager, there was Mariner, and Mariner did not use Golay codes. They used one of the other ones. My memory is that they used okay, so we can look up what it was. I think they actually used Reed-Solomon codes, but the efficiency of that scheme in terms of how much overhead was imposed by adding redundancy bits was somewhat high. And that's why they went back to Golay codes for Voyager.
Do all error correction codes work by comparing patterns that are potentially sent through 2 different channels?
No. So the way these error correction codes work is that we get a bunch of bits plus some additional bits, and then what we do is something akin to parity checking on all the bits that we received, and then we make some conclusions about errors based on that. So what's going to happen is sort of somewhat in contrast to the last bit of the question. All the bits are going to be transmitted once over a single channel, and then we look at what we receive based on that. Other questions?
Do you think that quantum error correction techniques will ever be as good as classical ones?
That's an excellent question. I think that from a mathematical point of view, I think I can say yes, but there is a practical, there are practical problems that come in, and you will hear all about them this week. In many ways, this week is all about this question. Well, a fundamental one is that today, in particular, if we compare ion trap quantum computers with superconducting quantum computers, it makes a huge difference whether you are on an ion trap and you have every qubit connected to every other qubit, or whether you are on a superconducting quantum computer where the coupling graph between the qubits is much, much closer to be a planar graph, and sometimes is a planar graph. And so this limits what one can do in terms of what needs to be done for error correction. So I think in classical computing, we are so used to that, if you like, every bit is connected to every other bit. And so that opens the door to get a lot done. And so I think that in the short term, for the purpose of making stuff happen with error correction, the ion trap quantum computers have a leg up. On the other hand, the superconducting quantum computers have advantages of their own, and I think that overall, no matter which quantum computer you look at, it's just more difficult to actually get the error correction going than on a classical computer. But as mathematically, it's sort of all the same. As long as we restrict ourselves to linear codes, the opportunities are the same. But of course, quantum computing has its own problems, and we will touch on them at the end of today and the rest of the week.
To elaborate on that last question, or on that last answer rather, how do we mathematically say that one linear code is better than the other, per se?
So we will get into this a lot today as well. So that will be covered. But in the end, the core of the answer is, how much better than duplicating 3 times are we in terms of how many errors can we either detect or correct, and how many additional bits do we need to add to our data to make that happen?
Are quantum error correction codes specific to the hardware they're implemented on? Is that necessary?
No. So the answer is no, and the reason is that when we are on gate-based quantum computers, like the ones from IBM and Google and Rigetti and many other ones, they all support any unitary operation. And so as soon as you support any unitary operation, then all this, whatever these are linear codes that people have developed for quantum error correction, it's all possible to do. So in a way, in that sense, all those quantum computers are the same. Then there are practical considerations about whether the qubits are connected this way or that way. That's practical stuff. But in principle, the opportunities are the same.
Does all of this apply equally to photonics-based quantum computers?
So I think that this question you must defer to the experts coming later in the week. I do not know the answer.
And the final question here, are single bit errors more common or burst errors?
Okay, that is an excellent question. This really requires to know what the situation is today with today's classical hardware, both for communication and for computers. You really need an electrical engineering professor. And so tomorrow we are lucky that Ken Brown has an affiliation in every department that's worth knowing about. And so you should ask him. He will know the latest on this. My knowledge about this is way outdated.
And that's
okay,
it. Thank you.
Many thanks. All right, good. So now we are getting to using linear functions to encode and decode. And so let me first of all go back to this basic idea of saying that that we have this set B of bits, and and we know that really this is, in terms of math, is GF2, the Galois field with 2 elements, which means that we can do things like addition. We can do plus. Some people like to call it XOR. And so it's really addition modulo 2 that we are doing here. And so we can do math on it. That's the point. And then whenever I see a 0, if I want, I can think of it as a little, this is like a little vector here. If I see a 1, I can think of that as a little vector as well, because I want to start to do sort of matrix and vector stuff on everything. And then when I said I have 0, 0, 0, today I like to simply think of it as a column vector. When I see 1, 1, 1, I like to think of it as a column vector. So that's kind of how I mathematically organize stuff. And so whenever we need to do math, it's all going to be in GF2. So whenever I have a code word, it's going to be a vector. And so let's now look at a situation here where we have k bits. So we start with that the data that we have is k bits. Okay, maybe I should write data explicitly here. So we have that our data is k bits. And so it means that in terms of our picture from before, maybe I could write down here something like data. Okay, so we want to do data. So here's our set of data, and that is now b to the k, a vector of k bits. And what I want to do is that I want to encode this stuff. So I want to be able to say, I want to map this over to some more bits that gives me some redundancy. So k is less to be equals, what am I saying? K is less than n. We're going to add some bits. So what does that mean? It means that over in Bn, we have a bigger set. So let's sort of draw a bigger thing here. And in there, we have the code words for the data. So so the encoding function will add some bits. And so so in some reasonable way, I can say that in here, I have the sort of the mirror image of the data, but now they're encoded. So now they're all, instead of being vectors of length k, they are now vectors of length n. So it means that here I can talk about the code words. And so so what we're going to do is that we are going to do this with a linear function. And so it means that right around here, I guess we could draw some kind of thing here. This is a linear function. And so so actually this is a, maybe not in purple. There's a thing here, which is a matrix. So this is a, it's a linear function. We know we can represent linear functions from vectors of length k to vectors of length n with a matrix. And so what people do is that they call this the generator matrix. And so we're going to always represent these linear functions with matrices. And what we want is that this is an injective function. So we just want to be sure that this thing here is an injective function, so that 2 different pieces of data get encoded as 2 different code words. That's really all we need to make sure. And so what you can tell is that given that g is a linear function, it means that if we look at the 0 vector over on the data side, it will always be encoded as the 0 vector over on the code word side. Just an observation. So what can we say about this generator matrix? So I'm going to always think of it that I apply from the left the generator matrix to some data. And so it means that this matrix here is, it's an, as you can tell, it's an n by k matrix. You show up with a vector of length k, and out comes a code word of length n. So that's where we are going with this. And of course, in our example, we can now sort of see what is actually g. And so so in, maybe I can sort of draw a little example down here. G is equal to 1, 1, 1. And the reason is, of course, that if we start to apply it, we do something like g applied to 0. So maybe something like this. Then really what we get is 1, 1, 1 applied to 0, or maybe like a little 0 vector, and then we get 0, 0, 0. And similarly, if we apply G applied to 1, it's really 1, 1, 1, and applied to not to 0, but to 1. And then at that point, we get 1, 1, 1. So that's how we can think of what we have been doing all the time today as really doing linear functions for encoding, this very particular linear function G. And so now people start to have some terminology because it takes some time to sort of write down all this. So there's a very succinct way. And so what people like to say is that for a code that encodes k bits into n bits, they like to call that, so this kind of thing here is an, let's call it an NK code. So for some reason they like to mention the size of the to space first and the from space second, but that's what it is. So n is bigger than k. So in this case here, what we have down here at the bottom is the case of we get everything encoded as 3 bits. We start out with 1 bit, so it's a free 1 code. So this whole thing is a free 1 code. And we can see that this makes sense because our matrix is a 3x1 matrix. So it's all good. So all the time today we have been talking about this 3x1 3,1 code. So okay, any questions about this point? So that's really that's sort of a single point on this slide, which is we are going to encode using a linear function, an injective linear function. We can represent such a thing as a matrix, and then the sort of the quick way of summarizing what code it is simply to first talk about the number of dimensions of the to space, comma, the number of dimensions in the from space. And that way we also know the dimensions of the matrix.
No questions that I can see so far.
All right, good. So now we are going into to detecting errors. So detection.
One
Yep.
just came in.
Yep.
You said G should be injective. Shouldn't it be bijective since we need to decode and go back?
Let me go back a little bit here. So the key thing is that it needs to be bijective on its image. So this is exactly how injective functions work, is that the space b to the n is much bigger than this thing over here. That's the image of b to the k. And so of course G is not going to be bijective on all of b to the n, but it will be bijective on its image. So we have sort of a very nice one-to-one going between these two, and then this stuff out here, that's a different story. Other questions?
That's all.
All right. So so the question is, how do we do this? So now what we're going to do is, we just had one linear function for encoding. Now we're going to have a second linear function for detection. And so we have our code words. And so it means that sort of very important to us up front here is this little set. So this is the one over here. So this little set over here is the image of bk under G. And so we're going to work with this space a lot. This is the code space. So let's just get that out there. So this is our code space. It's full of code words. And what can we say about every element of this thing? So the idea is that every element of this is something we can think of as, we can always think of it as, so some kind of element here is in the span of the columns of G. That's just how matrix operations work, right? But it's a very helpful today to think of it that way. So it's the span of the columns of G. So every element is a linear combination of the columns of G. And okay, so this means that we have a way of thinking about how do we get our code words. Look at the matrix and look at the columns. Now we want to decode. And so what we will do is that we will take up an interest in the rest of the space. So if you just sort of remember what we had this space here of, maybe that's not the best way of doing it. Let's do it this way. We have this space here, which is b to the n. And somewhere in there, we have this g of b to the k. But what about this other stuff? So we have lots of other stuff floating around out here. What do we do with that? And so, so I guess we can write this down as b to the n, except for the space of our code words. And so how many dimensions does this have? So this, I would say that we sort of carving out k dimensions there. So this thing is an n minus k dimensional subspace. That subspace is now going to be very important because the code words, if all we get are code words that are here, then everything is fine. But of course, the errors will be out in the blue somewhere. So whenever we get an error, it's going to be out here. And so we have, for the purpose of detecting errors, we have to take an interest in the blue space. So we want to get a handle on how to operate on that blue space. And again, just like before, the answer to how do we encode was a linear function. The answer to detect, the answer is going to be a linear function. And so we want to operate on this space. So what we do is that we say, let's find some kind of matrix that that we can somehow think of as describing something important about this blue space. So that's sort of what I will say initially, and then you will see that I'm working my way to connecting to the first hour of today. But so far, we just want to describe this blue things. And so, so what I will do is that I will get this idea that I will say that P is a matrix. And what I want is that the rows of this matrix, that the rows span this space here. I want them to span this space. Okay, so this means that if they're going to, if we just go for a matrix that has maximal rank, then it means that this matrix will have rank n minus k, of course, because we are trying to span an n minus k dimensional space. So so this means that in the end, the matrix that I'm going for will look like this. This matrix here will be a matrix that is n minus k, and then n. Okay, so the n is maybe needs some work. Then we'll talk about that. But this thing will be this size of matrix. And then I could as well just go for maximal rank, so we don't have too much fluff in there. So maximal rank. So it's actually a rank n minus k. So what does that look like for our example? So let's go back and go to our example. So in our example, we had that n was 3, k was 1, n was 3. So it means that for this for our example, we get this. So that means a 2x3 matrix. So this is just to say this is our example with duplicating everything 3 times. So we get some kind of 2x3 matrix. That matrix should have maximal rank, so it should have rank 2. And so this means that the rows should be linearly independent, and they should span this blue space up there to the right. And it turns out that the matrix that we can use for our example is this one. Let me just write it down here. So the following matrix would be a totally good one. There's sort of, one can do this in multiple ways. This is not unique, but this is totally good. Now comes an observation of what we get here, and I'm just going to do this observation for the example. The observation is that P times G is equal to all zeros, and you can see that if we do this for the example, then we get. So just going to the example here, we get that P was this matrix that I just showed. So it's the following thing, came out of the blue. G is 1, 1, 1. And then I think you can see that if we multiply these two together, we get something like, I guess we could say, I'm going to write it this way: 1 times 1, 1 times 1 plus 0 times 1. And then in the other row, we get 1 times, actually, want to be consistent. 0 times 1 plus 1 times 1 plus 1 times 1. Big conclusion is 0, 0. So absolutely correct for that. So we have made a good choice. And of course, we can also look at it in a different way. We can say, if we look at these two rows, it is actually true that they span the rest of the space that are not taken up by the code words. That's something one can check, so I'm not going to go into this. And the thing that we are working towards here is actually an if and only if. I'm going to state this as a little theorem about these two matrices. And so so now this is sort of the time to introduce some terminology. So we already talked about that this is our generator matrix. So so here we have, let me draw it this way. So here we have our generator. And then I'm simply going to maybe, as you have guessed, use the terminology parity matrix, parity check matrix for the other one, the one that we're going to use for decoding. So I'm going to do it this way. This is our parity check matrix. Here we go, parity check matrix. And so so what is the idea? So the idea is very much in the end summarized by this let's call it requirement or assertion or observation, PG equals 0. And so the idea is the following: the theorem says that for all elements of Bn, both the code words and any other stuff, what we want is that P times S is equal to 0. So it's equal to the 0 vector, if and only if S is in G of Pk. And so you can see that if we sort of take this back to the observation up here, then if we start out, if we sort of go in the right direction, from right to left, if we start out with a something that is in the image of G, and then we apply P to it, we will get 0, because P times G is equal to 0. And what we're going for here is then if and only if that we only get a 0 if S is one of the code words. And so so this is a way of saying that what we are getting here is a kind of a parity check, that if we apply a parity check to something that is a perfectly good code word, uncorrupted and everything, and you apply the parity check matrix to it, you get all 0s, which is exactly, if I go back to my example from before here, if we are receiving a code word that is completely uncorrupted, our error syndrome is just all 0s. That's kind of what we are seeing. And as you can see, any other code word that we receive, no matter what it is, will not be 0. So you can see the example here totally supports that this theorem seems to be right. It's if and only if. The error syndrome is all 0, if and only if there was no error. So so we go back here. So this means that so now what this parity check matrix is giving us is that it's giving us a handle on at least recognizing whether we have a perfectly good code word in front of us. And then the second part of the story is that it will also help us do something reasonable if there's a single bit error. And actually, but this can then be generalized to more errors, but now we've had single bit errors in our mind for so long. But it will help us do something when there's an error. And so we'll get to that. But before that, let me take some questions.
Is this theorem another way of stating that the subspaces are orthogonal?
I don't know whether this theorem is another way of saying that, but I think the two subspaces are certainly not overlapping. So I think that it is true that that if you take any vector from one subspace and another vector from the other subspace, they will have inner product 0. So whether this theorem exactly captures that, I am not totally sure, but it could be. I hadn't thought about this question. I think it'll take a little bit for me to sort of work through in my mind whether the answer is yes. Maybe somebody who is not in the middle of a lecture can work this out and say if the answer is yes or no.
Is the parity matrix unique?
No, it is not unique. So in particular, one could swap the two rows and you will still have a perfectly good parity matrix. Really, all we require is that the rows span the rest of the space.
How do we get the parity matrix? Is that pretty difficult usually?
Okay. That is an excellent question. And of course, there's a whole branch of classical error correction which takes care of that. So of course, in a way, we could say that we are solving an equation here that we just give me something that satisfies this, and we'll probably do quite well. But for today, I'm just going to punt on this question and say people know what they're doing to figure this out.
There's a question that would like you to elaborate how this matrix multiplication that you did, PG, how that ended up being 0 because the result on the right didn't seem to look like it.
It doesn't seem to look like it. Okay, let's, great. So it's always good to double check our math. You never know. So here we have, as far as I can tell, 1. Over here we have 1. And then finally over here we have 0. So it means that when we add these together, we get 1 plus 1 plus 0, which is 2, modulo 2, which is 0. So I think that this 0 checks. And then let's do it again for this one down here. We have 0 times 1 is not 1. It happens to be 0. And then 1 times 1 is 1. And then over here we have 1 times 1. That's also 1. And then when we add it up one more time, we get 2. Modulo 2 is 0. So I think this means that this one checks out as well. So I feel pretty good about this computation here.
Why is PG in this example not 2, 2? Oh, I see. It's asking the same question as the previous one. That was my bad. Moving on.
No, it's fine. So, okay.
P seems to be constructed from columns made out of error syndrome. Is that a rule or a coincidence?
No, it's not a coincidence. So actually, that's just bringing me to my next point, which I will now immediately do. So many thanks for bringing this up. So let me do a little bit of example here at the bottom, which will answer this question. So I guess we'll just go with our example. So we have G of so this is now our example G. So we just have a single bit that we are encoding, and we know that this space is 0, 0, 0, 1, 1, 1. That's our code words. So let's just for fun here apply our parity matrix there to each of them and see what we get. So P applied to 0, 0, 0. So this means we get hang on, just a second. We should not apply to 0, 0, 0. We should apply to some error matrices. So this means that we need to think about what is an error. So before I can do anything at all, we should think about what is an error. So I think this question will be answered a little bit in longhand, but it also means I need more space. So we have that this is our code space, and now let's get towards this thing about the error syndrome. So let's repeat. The question was that when we look at the columns up here, they look amazingly like error syndromes, like we had in the example many pages ago. let's explore this a little bit. So so it goes like this. So we have, let's say that we start with a code word. So it's something that lives in G of BK. And we want to model a bit flip. So so what is, maybe we want to model multiple bit flips. So so what does it mean to get a bit flip? And so given that we're doing linear algebra today, it means that we're going to add an error vector. So this thing here is an error vector. And of course, if it's an error vector with a single one and the rest of it's zeros, then it's like flipping a single bit in S. And so the sort of the notation I will use a lot from now on is that S prime is the corrupted code word. S is the real code word, and then S prime is corrupted by this error vector. So whatever you see here, I'm going to, every once in a while, I will need to talk about S and S prime, and it's always going to be like this. So what is E? So if we go to single bit flip, then we have 3 different E's. So they will come to, I'm going to call them E1, would do a bit flip on the first bit. E2 is going to do a bit flip on the second bit, and E3 is going to do a bit flip on the third bit. So we have that. And if you like, we can do sort of a geometric interpretation of these things. We could draw a little cube, which I will endeavor to do here. Let's see if we can get a cube going. And then that looks quite a bit like a cube. And let's now, so you can see the 8 corners of the cube. And so what we can do is that we can say down here, this is where I want to think about my encoding of 0 should rest down there. And then in the absolute opposite corner, that's where my encoding of 1 should be. And then what I can do now is that I can start to say, well, so I'm encoding 0 as 0, 0, 0. I'm encoding 1 as 1, 1, 1. And then the idea is that if we move away from 0, 0, 0, then if we move away by 1 error vector, then we just move to one of the sort of the nearby corners. And so we can draw those as maybe, how about we say up here we have the one with 1, 0, 0, so the single bit error there. Down here we have 0, 0, 1, and then over here we have 1, 1, 0, 1, 0. And then maybe just to make the colors different, I'm going to say 1, 1, 1 is blue today. And then we can do, again, single errors up there. We have something there with the first bit flipped, second bit flipped, and third bit flipped. And so the idea is that what we're really seeing here is a picture of this space from before, that if we think of maybe I should just draw a circle around all this. I'm going to draw a gigantic circle around all this. So we have all the possible bit vectors of length 3 are all there. And then what we see is that the 2 elements of this G to the B1 spread out quite a bit. So they in some sense, we put them as far apart as we could. And then there's some kind of division of stuff going on here, where if you move one error away from one of them, then you don't get too far. You don't get mingled with the other one. And that structure is really kind of what we're going to cook soup on the rest of today, which is to get into a situation where the code words are spread out, and then a single error will not be too far, and we would be able to sort of bring it back to where we came from. So if we are here, we'll be able to bring it back here, and if we are here, if we are anywhere over here, we can bring it back here. That's kind of where we are going. So we need to get some concepts going to really hammer this home, but that's where we want to be. Something like this. Okay, so we still have not answered the question of the parity matrix, but now we're getting to it. So what I will do now is that I will apply the parity matrix to S prime. So let's just reminder, we have that S prime is equal to S plus E. So corrupted code, okay, this doesn't look too good. S prime is the corrupted code word. S is the code word that the sender actually sent. and E is the error vector, and now we apply P to S prime. Okay, so this is P applied to S plus E, and so that's, of course, P is a linear function, so this means that this is P applied to S plus P applied to E, and aha, so S is a real code word that was produced by G, and we know that this thing here is then therefore 0. That's the whole design of the parity matrix, is that this thing is 0. So so very importantly, this thing here is 0. So it means that down here we are really just left with P applied to E. And this is the generalization of error syndrome. This thing here is what we will call the error syndrome. So that's the sort of the general case. And now we can look at what is the error syndrome then. And then you will be unsurprised to find that if we do P applied to E1, so maybe I should just write out the matrix. So we get our P matrix again here applied to E1, which was 1, 0, 0. And now you can see that what we are doing here is that we're really just picking out the first column of P. So we have that this thing is there. And then we can keep going and do the same thing for the other ones. P applied to E2, we do it again. Here's P, here's the second error vector, and again we get 1, 1, and again here's our error syndrome. It's the second column, and just for completeness, let's just do it one more time for the third one. We get our parity matrix, and we get our third error vector, and we get exactly the third one. So here we have this. So the very short answer to the question is yes. What we see is that these columns are the error syndromes. And so this works beautifully because we are doing single bit errors. And then, of course, once we generalize to deal with multiple errors, then it becomes more general. But right now, as long as we do single bit errors, it's a beautiful observation that the columns of the parity matrix are exactly the error syndromes. Other questions?
The 0 vector is always a code word. Is this intentional?
That's just what you get when you're doing linear code. That linear functions have a tendency to always map 0 to 0. And so given that 0 is perfectly good data, then you will always get 0 as a code word. So that simply comes with the business of doing linear code.
Here's a question I'm not sure I understand. Isn't modeling a bit flip the same as causing a bit flip intentionally in systems?
I think that my answer kind of stays the same as for a similar question earlier, is that today I'm not thinking too much about whether the bit flips are intentional or just happen by nature. The business today is to dealing with them. So I have no further interesting things to say about this question as it is.
If 0 is equal to PE, wouldn't that make it part of G of B to the K?
Yes, absolutely. So that is exactly right. So that's exactly what this theorem here is saying in the forwards direction, that if you have that P applied to something is 0, then that something must be in G of BK. So the question is about the forwards direction, and the answer is yes, that's exactly how it works. Other questions?
That's it for questions for now.
All right, very good. So so this means when we're looking at this picture here, what we see is now everything coming back with the story about parity checks. And so what we're doing here is that we are representing the two parity checks from earlier when we just did it by sort of back of the envelope as two rows of the parity check matrix. And so so just like before we were saying, you notice that these three error syndromes are all different. And what does that mean? It means that just like before, it means that we know which error it was. And so it means that we can we can now think of a function that then maps back. And so for this situation that we're in, we can sort of write it in the following way. Just make a sort of a corner up here for describing the situation we're in. That we can now, let's call it, fix the error. Well, at least the first step to fixing an error is to know what the error was. And so so what I will do is that I will define a function q here that maps an error syndrome to the error. And so you can see what it should be. So q applied to the error syndrome 0, 1 should map it back to E1. Q on the error syndrome 1, 1 should map it back to E2. And similarly for the third one, Q on error syndrome 0, 1 should map it back to E3. So so that's just how we say, we see the error syndrome, all the error syndromes are different. So this means that we can now recover what the error was. And this then allows us, once we have this Q function, really what's going on here is the following observation, that that if we have an error syndrome, PE, and we apply Q to it, it'll be E. So it's like we get the error syndrome. It's very important to us because of this calculation over here. And then we know that if the error syndrome, if everything is designed well, so the error syndromes are different, then we can apply this Q function to recover what the error is. And that then means, and now comes sort of the crux of all this, this means that if we receive S prime, then how do we get back to the actual code word? If everything is working correctly, then it means that we can take S prime, then we can apply P. Of course, that was the calculation we did before. We're going to get an error syndrome out of that, and then we can apply Q to recover the error. And then, so it means that if we do this, then we know that from the calculation on the previous page that P applied to S prime is really the error syndrome. And then this whole thing is by design the error. So this means we get S prime plus E. And of course, S prime is just S plus the error. And then that's because the two E's cancel out. I guess we can take the time to write this out in full. The two errors cancel out modulo 2, so we get S. So at the end, we get the message that was sent, the uncorrupted code word. And so all of this, because we have a very good design of the parity matrix, the parity check matrix. And so the way we can sum this up is as two little theorems that sort of sum up really a lot of what's going on in classical error correction. So just to get a lot of what I've said just into a few words. So the first theorem here talks about error detection, and what it says is that error detection is possible. So here just important that the operative word here is detection is possible if and only if every error has a non-zero syndrome. So non-zero as in it's not all zeros. So the idea is very simple. We go back to this calculation from the previous page, apply the parity check matrix, see what you get, and if it is exactly this case that good code words are mapped to all zeros and everything else is mapped to non-zero, then clearly it means that if you see a non-zero syndrome, it is an error, and you should ask for repeat. So it means that detection has to do with non-zero syndromes. Then the other theorem is about error correction. So now we are moving on to error correction, and so error correction is possible. And so now we are sort of picking up on the example that we just had. If and only if. In this case, what we need is that the syndromes are unique. So every error has a unique syndrome. And so, so that's essentially the example we just saw, that all these different errors all end up with a unique syndrome, and when we know which error happened. And so I would say what you have right here is sort of the whole basis for classical, sort of the thinking about classical error correction in a nutshell. It's right there in these two theorems. And sort of another way of thinking about this theorem here is that what we need to detect an error is that it never happens that an error changes a good code word into another good code word, because if that's the case, then the error would have a zero syndrome. We need good code words to be changed into corrupted code words. If that's what's going on, then we can detect the error with applying our parity matrix. So this means that in practice, modeling the error is very important. And so what's going on with these two theorems really is that that we need to decide what is an error. And so what we've been looking at so far is that an error is a single bit flip, and we can model, for the case of sending 3 bits, we can model that as saying that the errors are adding 1 out of 3 vectors. And then what we need up here is that all of these 3 vectors by the parity check matrix are mapped to non-zero. And down here, what we need is that those 3 vectors are mapped to something different. So they should all be, whatever the outcome of applying the parity check matrix to the errors should be different things. And so then one can say, okay, so does that mean that there's some errors that we cannot correct? Of course. So then we're back to this thing that up here, if one code word is mapped into a different code word, we cannot detect the error. And down here, again, if an error just makes too much change, then we may end up that there's some other code word that gets mapped to that can be mapped to the same thing, and then we don't have a unique syndrome anymore. So it means that really what one can say is you can work your way backwards. You can say we want these 2 theorems, and then we can, for a particular scheme that we have in mind, we can work out which set of errors actually satisfy these theorems. Okay, any questions?
Since these are both bidirectional implications, does that mean one theorem implies the other?
I don't think so. I think they are quite separate, but the thinking behind the two are quite similar.
Then do we need both for truly correct error detection?
So it's really just 2 different topics, right? If all we want to do is detection, we just use the first theorem.
I see.
If all we want to do is correction, we use the second theorem. So I wanted to put them on the same page just to be very clear about what we have in front of us here. So the lovely thing is that it all boils down to a linear function.
These 2 theorems are just relating to the case of a single error, right?
No, so they are general. So the 2 theorems here are completely general. And so what I'm saying is that depending on what sort of scheme that we have, we can, let's call it, support more or fewer errors. And so that was kind of the intention with the comment before, that you can take a particular matrix, and then you want to say, I want this matrix to satisfy these 2 theorems, and now you can sort of back out which errors are supported. And so, for example, if you start with the idea that I want to replicate 3 times, so that's my idea for a code, and then you can ask, okay, great, which errors can we now correct? And then you can say, well, I want this theorem to be true, and then you can work your way backwards and find that all you can correct will be single bit errors, but not 2-bit errors.
What is the explicit form of Q in the example discussed? Is it always PT?
So this is the explicit form of Q for our example. But in practice, it's like a lookup, that you make a little lookup table that says, from this syndrome, it's this error. So it's not a linear function. It's just like a little, it's like a lookup.
Just to double check the terminology, code words refers only to the valid states in our example.
Yes,
0,
yes.
0,
When I
0,
say
and
code,
1, 1,
so
1.
I try to distinguish between that we have data over here, and data always gets mapped to code words over here, but then there's this bigger set of stuff. And so what we have out here are the corrupted code words. At least that's the terminology I used a lot today.
Back to the theorems. For error correction, can one of the errors have a zero syndrome?
No, the syndromes will always be non-zero. Yeah.
Does Q have to be the inverse of P?
It's a left inverse, right? So it's like we always design it this way here, that P is a left inverse of P. So that's the fundamental thing we gotta have for all this to work.
Is there an example in the classical world where these theorems cannot be met, so the error cannot be corrected?
One can always duplicate more. If you come and tell me that you want to correct something like free bit errors, then I will just add enough. I will just, for example, replicate enough times. If you want to correct free bit errors, then I will replicate enough times so that we can correct that. So there's always a bigger code. No matter what you want to correct, there's always a bigger code. Whether that code is more than we want to use, that's a different story, but there's always something for you.
In actually realizing this classical error correction, do people physically perform the math on the left?
Yes, of course.
If the syndrome is non-zero, then error correction already includes error detection.
So in a way, yes. So there's something about that. I think that at the intuitive level, the answer is yes. That it's a stricter requirement to say that we want the syndromes to be unique than to say that they are non-zero.
Is it true that Q cannot be represented as a matrix? Hello? Did I freeze or did Professor
No,
Palsberg?
Jens is frozen. Let's just give him a minute. I think he'll, yeah, here he is.
Yeah, okay. That's great. August, you're back.
Okay, the question was, let me grab it again really quickly here. Is it true that Q cannot be represented as a matrix?
Yes, it is true. We should think of it as a different kind of beast. It's just like a function, if you like. One can easily show that there are cases where Q simply cannot be a matrix. It would violate the laws of math.
If the phase flip error has the same error syndrome for different phase flip errors, does the second theorem still hold in this case?
So August, I think I will pause the questions for a moment and press on, because I have my third topic coming up that I feel that we're beginning to approach with the questions that are coming up. So I just want to talk about it, which is,
Sure.
What is the reason why these linear codes work well? And in a way, the secret to this is embedded in this picture here, which is that what we do is that we spread out the code words so that between these two, there's quite a lot of distance. The 0, 0, 0 is quite far from 1, 1, 1 in some sense. And the question is which sense? And so this is what I will define next. And so we're now entering the third and last bit of the lecture today. So what I will do is that I will say, let's look again at Bn. So everything we have over there on the target side, and let's define a weight on these bit strings of length n. I'm going to define a weight. It's the weight is a natural number, and the idea is that plainly that if I apply W to S, what it really is that it's the number of non-zero entries in S. So that's it. It's a very, very simple definition of weight. So it means that the more ones you have, the more weight you have. And so now what we can do, based on this idea of weight, we can now define a famous thing called the Hamming distance. The Hamming distance is talking about the distance between, I guess, let me just make this explicit. Let's say that we have an S and a T over here in Bn. And what I want to do is I want to define the distance between S and T. And that distance I can now define as, well, so the natural thing is to say, this is sort of what we normally do with vectors, is that we would take S minus T, and then we take the weight of that. And that would be sort of a very reasonable way of saying we have this difference between S and T. That's sort of the way to go between S and T, and then how much is that? That's our weight. Of course, because we are working in DF2, this S minus T is the same as S plus T, and that is the definition of Hamming distance. And so one way to think about this is that the distance between two things, S and T, two bit strings S and T, is the way we can interpret this is the number of bits that we have to flip to change S into T, or the other way around, to change T into S. And this is a metric. So this Hamming distance is actually a metric. So it satisfies that the distance is 0 exactly if the two bit strings are equal, and otherwise it's greater than equal to 0. It's totally symmetric in S and T, and we do have a triangle equality. A triangle inequality, I guess it is, a triangle inequality. So it's totally a metric, and so it's a very fine thing to call a distance. And so now what we can do is then to use this idea of distance to start to talk about how far away are these different code words from each other. And the way I will talk about that is that I will define D of G, sort of the distance of the code words generated by G. And so what I really want is I want to spread out the code words as much as possible. So it means that I'm interested in, you know how it is, any chain is no stronger than its weakest link. And in this case here, whatever two code words end up being really close, that's the weakest link here. So so it means that I'm interested in some kind of minimum of distances. So I will take the minimum of distances between two S's, between an S and a T. And so S and T are both code words, so they both live in T to the BK, and I want them to be different. So I'm interested in distances between two different ones. And so the intuition here is that we have our BK, BN over here, but with, of course, some kind of BK embedded in it. And we start to look at all the code words, and we say, well, here they are. And then it's like, oh, the weakest link is here. These two are really close. And so that thing, that distance there will be, the sort of the distance between them is D of G. And so the more we can spread them out, the more we can spread out the code words, the bigger this minimum distance will be, and then the whole point is the better chance we will have at correcting code. In the spirit of the cube that I showed before, that for example there, one single error will allow us to bring it back to the code word that was the uncorrupted code word. So so what is this actually? So let's just work on this expression here a little bit. So we can sort of work on this and say, so we have the definition of the distance. So let's just write this out. So the distance is equal to ws plus t. So that's I just want to write everything so we get it right. Still, s is different from t. And of course, when it comes down to it, every element of the set of the code space, of the set of code words, is a sum of two vectors. So this thing of saying a sum of s and t, that's like everything there is a sum of two vectors. And by saying that s is different from t, really the only thing we are saying is that s plus t is not 0. So so it means that talking about the weight of all these s plus t's is really the same as just talking about the weight of any element of the space over there. So I'm just going to call that any element. I'm just going to use the name set. And as I said, the only requirement now is that set is not 0. So it's like, oh, okay. So this means that we can just look at the weight of all the code words and just find the one with the minimal weight. And that's this distance that we sort of illustrated up here. And so we can do that for our example. So just to say what is the weight of everything. So let me just go back to our example. And so what do we see? We see that the sort of d of g is, well, so what is that? So it means that it's the, let me just write this out to sort of be sure that we know what we're doing. So it's the weight of any code word where, what's the code word for the example? So that we only have 3 of them, 0, 0, 0, and 1, 1, 1. But of course, we also have the condition that it cannot be all 0. So it cannot be 0, 0, 0. So this means that really what this is, that is the minimum of the weight of 1, 1, 1. Okay, what's the weight of 1, 1, 1? That's 3. So it means that we get that the two code words are spread out by 3. Well, that's true. So if we verify this by hand, we can see that you need to switch flip 3 bits to get from 0, 0, 0 to 1, 1, 1. So this 3 is totally believable. The good news is that this always works. So you can plug in any matrix you like and do this calculation, and you will get the minimum distance between any two code words. And so the terminology that then, so this is like the crux of this here, the terminology that people then like to use is, we want to talk about a code as an NK code that maps k bits to n bits. But then the third thing to know about it is, and what distance between code words do we get? And so this is the third component that everybody cares about. And so you can see that what we have been doing so far in our example is we have been studying 3, 1, 3. And this, the key thing is that this 3 is this 3 down here. So we have so all the time today we have been studying a 3, 1, 3 code. So so what we get is the following situation. So now that we have that it's 3, we can start to just sort of think a bit more deeply about what's going on. So so we have the following. If we have, again, a corrupted code word s prime, that was really a code word s corrupted by an error vector e, now we can start to think about how much was changed to get from s to s prime. So we'll do the Hamming distance from s prime back to s. And so what is that? Well, of course, that's equal to the weight of s prime plus s. And of course, s prime is s plus the error vector plus s. And then the two s's cancel out. So that's really just the weight of the error. And so really what's going on is that when we are moving in our space, so we still have our b to the n over there, and we have s sitting somewhere, and then what happens is that s gets kicked over to be s prime by e. And what's the distance there? The distance. So now we can think of that the distance that we go is actually we can just sort of draw it like this. The distance that we go is the weight of the error. So this is sort of maybe a simple observation, but it allows us to now state something very nicely, which is so let's say that we are in a situation where, just for a change, instead of having 2 code words, we have 3 of them. So let's say that we have 3 code words here. So this is so red equals, these are the code words. So these are the uncorrupted things. And then what we are doing here is that we are saying that around each of these is like a little sphere, which normally is called the Hamming sphere. So the Hamming sphere goes like this. So these are the elements that we can bring back. And so what we need is that we need those to not overlap, just like we saw in the cube, that with single bit errors, we get like 2 parts of the cube that don't overlap. And so the idea now is that if we are here, then we will be able to bring this back here. If we are here, we'll be able to bring it back there. But if we happen to be somewhere else, so maybe we are somehow we landed out there, then there's no way we can correct that. And so what happened there is that intuitively, that maybe this thing came from that we got an error on this red one down there, but we could also have gotten it by some error that happened there. And now we are too far from either of the 2 red dots to know which one we should go back to. And so, so this means that the interesting bit here is how big is the sphere? How big is the Hamming sphere? So let me just say that this thing here is normally called a Hamming sphere. We got to give credit where credit is due. And so what really matters here is the radius of the Hamming sphere. And so we can express this radius in the following way. Let me just draw here that here we have this thing that I will say is radius r. And what is that we want? We want to be able to correct errors. And so so you can see that we take the minimum distance between the red dots, that's DFG, and then we say -1 divided by 2. And that way, clearly we ensure that these things don't overlap. And so in our case, you can see it all works out beautifully. For our example, we have that, so for our example up here, we have that DFG is equal to 3. So it means that when we do DFG divided by -1 divided by 2, we get 3 minus 1 divided by 2, which is 1. And that's exactly saying we can correct 1 error, 1 bit flip. So very, very nice and straightforward math to say, if you can calculate this D of G, then we can then use this little formula down here to then work out how many bit flips can we correct. Any questions?
Sometimes in LDPC theory, people define the code distance as the minimum number of 0 entries in a code word. Is this an identical definition or a weaker one?
I think that so in a way there ought to be a dual between counting the number of ones and counting the number of zeros. But somehow it's like it's been with me since I was an undergraduate student that we always count the ones, and I didn't notice that there was this other strategy of counting the zeros. So at the moment I won't swear on whether it's totally equivalent, but it seems to at least be duals of each other.
If S and T are code words, is it always the case that S plus T is a valid code word?
Yes, exactly. So that was also what we used in the calculation before of the Hamming distance. So when we go back to this calculation here, when we look at this step here, we are exactly using that when S and T are code words, then S plus T is also a code word, and vice versa. That if you find a code word, you can always decompose it into a sum of 2 code words. If nothing else, the code word plus 0. Other questions?
I know that W of T for any T not equal to 0 imposes an upper bound, but how do we know that this upper bound is strict?
So this would take a little bit of a construction of saying that let's say that we violate this radius there, and then in some sense the question could be seen as a can we do a constructive proof of that there is such a point out there. So this can be done. I'm not prepared to give this construction today, but yes, it can be done. So it is strict.
Could you describe a little more how R is equal to D of G minus 1 over 2 ensures that the Hamming spheres don't overlap?
Yes, absolutely. So let's just continue the illustration here a little bit and say that the distance between these two, for example, is let's say that this is the two that are the closest. So that's D of G. So we looked at all the different code words and we found out these are the two that are the closest. Maybe there's some other ones that are also that close, but these two are really quite close. So then that's a number. So D of G is a natural number. And given that the two code words are different and D is a metric, we know that this distance is non-zero. So D of G is some number 1, 2, 3, whatever it is. Okay, so now we need these things to not overlap. And of course, distances here from a code word to a corrupted code word, again, are measured as natural numbers. And so it means that if we were to go with, say, just a little bit higher, let's say that we cross out the -1 and we just add a half to this, then we would get into a situation where there would be something which is right here in the middle. So I'm going to draw that sort of what I think of as right here in the middle, where we can get there by going half the distance from one of them. So we could go like this, but we could also go half the distance from the other one and you meet in the middle. And so it means that we need the radius to be just a little bit smaller than that. So we subtract a half.
With 2 code words, we used a cube. If we had 3 code words, would we use another vertex as a code, but in a higher dimension?
I am sorry, I need a bit more detail to understand this question.
I think it's asking in the previous 2 code word example, or we were looking for we had 2 code words out of the 6 possible strings. Yeah. And we assigned, those were opposing ends of the cube, right?
Yeah, yeah.
And if we wanted 3 code words, do we use another vertex of the cube, or do we use a higher dimensional structure, not a cube?
Yeah. So we would have to do a cube in a higher dimension than 3 dimensions. Exactly. Yeah. So we go to a 4-dimensional cube. Exactly. Other questions?
Hold on, I'm filtering. There's a question from earlier that I thought was good. Can you elaborate a little bit on the question about Q not being a matrix and why it can't be a matrix?
I can, but I want to punt on this question because I have other things I want to say. But you can sit down and do a little calculation where you say, let me assume that Q is a linear function, so it can be represented by a matrix, and then you will see that you get in something start to break at that point.
I think this next question is somewhat related to that. Is the error syndrome space not a linear space? Otherwise, the map Q cannot be linear. The real question is whether Q of 1, 0 plus Q of 0, 1 is equal to Q of 1, 1.
Aha, that's an excellent.
Syndromes back to arrows.
That's an excellent question. So I think that one way of saying this is if you take 2 error syndromes and add them together, do you always get an error syndrome? That would be one consequence of this. I actually don't know. I think that this is a very this has a known answer, but I don't remember the answer right now.
Hamming distance is pretty nice, but could we use different notions of distance, and how can those be useful?
Oh, Probably, but given that we are doing bits here, I think we don't really need another distance. But if somebody has a different distance, that would be fine. I think that one could probably do something. But it turns out Hamming distance is as long as we're using these bit vectors, it's exactly what we need.
What guarantees us that the sum of two code words is another code word?
Because we are using the linear function g, and so we know that every code word is in the span of the columns of g, and so so it means that we are already looking at that everything is the linear combination of these columns, and if you add two such linear combinations together, these columns, you will still get a linear combination of the columns. That's the reason.
Is the radius d of g minus 1 over 2 for all code spaces, or does it depend on n or k?
No, it's general. So this is a general. That's the lovely thing about using the Hamming distance, is that you get this single concept. So whenever somebody says I have this code that has this minimum distance of, say, 5, then you can immediately say, oh, okay, so this means that 5 minus 1 divided by 2 is 2. So it means that I can correct 2 errors, 2 bit flips, without knowing anything more about the code. The code can be incredibly creative and never seen before, but you know immediately that it can correct 2 errors.
If the Q is not a matrix, i.e. not linear, are we still using linear codes?
Yes, so the point here is that we are using linear functions for encoding and for detection. And then for the job that Q does, which is sort of the correction part, we are not using linear functions, but that is okay. What all we need is that Q does the right thing for the error syndromes.
Does the answer to the previous question imply that d of g is always odd?
No, d of g can be even. So in fact, if we go back and look at the code that does 2 copies instead of 3 copies, so 2 copies of every bit, then clearly we still have only 2 code words for a bit, 0, 0, and 1, 1. And then in that case, d of g is 2, and it's even.
Can this radius be a fraction? And if so, how does that make sense?
It just means, again, if we, let's just elaborate a bit on the example from before. So let's say that we look at this code that copies every bit like this. So we have that g is doing this stuff. And so the distance in this case is the distance between 0, 0 and 1, 1. So that's clearly 2. And then when we look at this radius and say that's d of g minus 1 divided by 2, then we're going to get 2 minus 1 divided by 2, which is a half. And so what is this saying? It's saying that we can correct half an error. Okay, so we don't have half errors. So it really means that we can correct nothing with this code. And that's exactly the intuition from early on. We can use G to detect errors, but we cannot use it to correct anything. And so if you do a different example, so let's say that you have a different example of G is something, and you end up that R is 3.5. That's just another way of saying you can correct 3 errors, but not 4.
And I think the final question here is, what are the advantages or disadvantages of a nonlinear code?
I don't have a good answer for that. So it's like today I filled up my brain with stuff about linear codes. So I kind of left the nonlinear codes behind. But clearly, people are smart and they have all kind of ideas for how to do classical error correction. And some of those ideas are just not linear. And so so that just brings in new ideas. The goal is always the same. The goal is to be able to detect errors and correct errors, and there are many different ideas for how to do it. Okay, so now I want to address a question. That's something that I promised I would address, which is, I will frame it in the following way: is use of our favorite encoding function G, whichever one it is use of G better than sending raw data? That's really the question. Is it better than sending raw data? So to be able to address this question, I'm going to, and do it in a few minutes, I'm going to make some assumptions. The first thing I will assume is that bit flip has a probability. And so I'm going to say that the probability of a bit flip is P. And this is the same for all bits. So it's like this uniformity assumption. It's just always P. All bits flip with the same probability. But I'm going to do more. I'm going to say that that bit flips are independent. And so that's just so that I can use the usual thing in math, that if you have two independent events, you can multiply the probabilities. So that's my two assumptions here. I'm just going to assume those two things up front so that I can do easy math on the red question. And so let's do some math. So let's go back to our free code. And let's take a look at whether it's better to use that code than to send the raw data. So that's really all the way back to this question of, should I send free emails with the promising the $100, or should I just send a single email with and hope the best? What should I do? So that's what we will work on here. So what I will do to make progress on this problem is that I will say, what is the probability, if I'm using this free code, that at least every time I send free bits, that at least 2 of the free bits flip? So that's like a bad case. So I'm sending free bits. I'm really hoping that either one bit or no bits will flip, but the bad case is that at least 2 of them flip. So that's not good. So if that's the case, then how often does this happen? Well, so maybe exactly 2 bits flip. So that would be P for that 1 bit flip. P squared means 2 bits flipped. Of course, this can happen in 3 different ways. And then the third bit does not flip. So we multiply by 1 minus P. Or all 3 bits flip. So we have to add the case where all 3 of them flip, which can only happen in one way. And then if we do a bit of math on that, we can see that we have 3p squared. And then we also have minus 3p cubed plus 1p cubed. So that's minus 2p cubed. So that's our formula there. And then, of course, now we can compare that to if we just send raw data, we just send a single bit. What's the probability that that bit flips? So that's the bad case there. It's just bad if it flips. So this means that what we need to do is that we need to compare this 3p squared minus this. And really what we want is that this is less than P. If G is a good code, if it's better than sending raw data, then that thing on the left should be less than P. And so let's just assume upfront here that P is something real. So it's not 0. So the errors are possible, and it's not 1. So there are really times when things go well. And then now we can start to do math on this. So if we just do a little bit of math on this, we can see that this is the same as just moving everything over to one side. Then we get that this is something like, okay, maybe we knock off 1p. Let's just knock off 1p everywhere. Then we are down to 2p squared minus 3p plus 1. I think that's about right. So I knocked off 1p and moved everything over to one side. And the reason I can knock off p is that it's not 0. And then, of course, at this point, we can use the quadratic formula. And what we end up getting is that p is either less than a half or p is greater than 1. That's just sort of if and only if plugging into the quadratic formula. But of course, we know that we just assumed over here that p is less than 1. So this case is not going to happen. And so we are left with that if p is less than a half, then it is better to repeat 3 times than sending the raw data. Or in terms of my email, if the chance that the channel will corrupt my $100 to $1 million. If that happens less than half the time, I will be better off repeating my email 3 times. That's the message here. So okay, so that's the case of email and $100. But let's look at some error rates of P that are more common in quantum computing. So let's go and look at something like so let's take it again just to write it over here. So we're looking at oh, maybe I just write it. You can all remember the formula. So we have this bad situation here is described by 3p squared minus 2p cubed, and then over here we have p, and then so what cases should we look at? So for quantum computing, something like 0.1. Okay, so that would say that that we get an error rate. Errors happen with probability 0.1. That's a little high. What about 0.01? That's more in the spirit of the error rates that I talked about for the IBM quantum computer earlier. And so it turns out if you plug this in here, you get that the bad stuff happen in 0.028, and so clearly that's well less than 0.1. So now it's like quite good. And if we go down to the error rates that we talked about, that's sort of closer to something like 1%, then this formula over here gives something that's well less than 0.01. It's actually this. So I would say that this is well less than. So so the lesson here is that doing this repetition of doing 3 copies of everything is already a great win if our errors happen with something like probability 1%. And if you can get it below 1%, then everything is even better. And so just to mention Eric Hudson, who introduced me this morning so kindly, he has ion trap qubits that have a spam error, spam reliability or spam error rate that is, so the reliability there is 99. Last I saw 99.97%, maybe higher today. And so it means that the error rate there is really in the neighborhood of even lower than 0.01. And so this is something that's really quite realistic, that if we are down in sort of quantum range of error rates, then it's way better to duplicate 3 times. And then, of course, then we get back to this thing, yes, but duplicating 3 times really seems wasteful. So if we are talking about our free one free code, if we are scaling that to say, I want to send 4 bits, then this is like saying I'm working with a 12-4 free code. So this is saying that to send 4 bits, you really have to send 12 bits, and then you can correct 1 error because because this minimum Hamming distance is 3. And so it just starts to really seem wasteful. And so the question is, and this is sort of the final question that I want to address today about classical error correction is, so can we then actually do better? And this is really what the whole field of classical error correction is about, is to do better. And so so what I want to do is that I want to just let it fly by on the screen here, a different code, which is instead of 12-4 free is 7-4 free. And so the idea is we still want to send 4 bits, but now we can do it with sending 7 bits. Encoded as each vector of 4 bits, we can encode it as a vector of 7 bits. And we still have a minimum Hamming distance between the code words of 3, so we can correct 1 bit flip. And so just to give you a sense of what this looks like, so it means that to get going on 7-4 free, clearly we need a 7x4 matrix, and I just want to show you what this kind of thing can look like. So we are lining up a 7-4 matrix, and so we should expect that there's some interesting things going on. And of course, matrices in a way look very nondescript when you look at them, but here is exactly a matrix that will do the job, and then we can do some calculations, and it turns out that a very nice parity matrix, which then will do the job of being parity matrix for this thing there, is Well, so what is it? So we need clearly 3 rows because the leftover space has dimension 7 minus 4, which is 3. And then we need those rows to be sort of nicely spanning what we need. And it turns out that if one defines it the way I have decided to show it today, it comes out like this. So here we have, as we want, we have that PG is equal to 0. And so we have that the main thing is there. And as it happens, the code, if we look at it, really has minimum Hamming distance 3. And one way you can see that is sort of intuitively, if you take this column here, and you take this column and add it to this column here, you can see that these 3 ones are left over. You can try other combinations, but you always end up with that no matter which code word you construct, there will be 3 ones. And so that's the 3 that we have here. So the minimum distance is really 3 between these. And so so a much better choice. If you go with this code, much better choice. Then you really have in code, you're just sending 7 bits instead of sending 12, as if you had done then that you would have done if you had used the other code. And then just to here at the end return to Voyager. So Voyager, both Voyager 1 plus 2, they used Golay codes, and the Golay codes that they used was, as it happens, 24, 12, 8. So that was actually on those spacecrafts. And so you can see what we're doing here is that now we are down to, if we want to send 12 bits, we are sending 24. So it's not too different from our repetition scheme. If we just use this original one where we encode every bit as 2 bits, then we would still have the same situation that we would do. We would when we want to send 12 bits, we would send 24 bits, but that one would only allow us to detect errors. Here, because we have minimum Hamming distance of 8, it means that we can actually correct. We can actually correct. Not, first of all, we can correct something, but we can correct 3 errors. And of course, we can detect 7. So if we can detect 7. Okay, maybe I should not write 7 factorial. That'll just be confusing. But we can detect 7 errors. So you can see a huge improvement over just duplicating every bit. And so one of the very first ideas of error correction was actually used on the Voyager. And it's really a good one. Very good sort of, what should we call this? Total bits sent to payload is quite good. It's 24 to 12. So this is really rounding up what I want to say about classical error correction. So you can see that in the end, it's all about that we use a linear function to encode. We use a parity matrix to detect errors. We design all of this so that the product of the parity matrix and the generator matrix is all 0. And then the whole idea is that if all the error syndromes that we get by applying P to a possibly corrupted code word is always non-zero, then it means that we can detect errors. And if all the error syndromes are different, then we can correct errors. And then the Hamming distance will then tell us how many bit flips we can correct. Like, for example, with this Golay code, sometimes it's 3. Any questions?
Could you hypothetically include here the probability of an error happening due to the replication step?
Yes, so that whole thing is really what this calculation is about. So when I got here and I do this calculation, that is really saying that now that we have 3 bits, there's a bigger chance that now there are more bits that can flip. And so so this calculation is about saying, okay, let's take this into account. and then do this comparison up here of saying, is it still better to replicate and expose us to more errors than it would be to just send the raw data? So this is where we end up with this thing with something about a half down there at the bottom. Other questions?
It seems correcting for classical bits using qubits is quite feasible. Are we limited by nearest neighbor coupling in superconducting qubits, such that we still care about the T1?
That is an absolutely excellent question, and you should ask that. That is exactly what the topic of surface codes is all about, Wednesday and Thursday. And I do have an opinion about what the answer is, but I'm not going to say it. I want to wait and hear what the answer is from the two masters of surface code speaking on Wednesday, Thursday.
How good is the assumption of independent error probabilities?
It's not good at all for quantum computing. It turns out that for quantum computing, if you look at, say, IBM is very good at publishing their error data, and you can be pretty sure that the error rate for every qubit is different from the error rate of the other qubits. So it's not good at all. In practice, it's not super different, but it's really remarkably different.
Do you need to determine a code for the total number of bits you need to send through the channel?
No. So what you do in practice is that you break up into two chunks. So in this case here, of the Golay code for Voyager, you break up everything into chunks of 12, and then you encode that, and then you take the next 12 and you encode that. That's how it works. So this is why people like to talk about block codes, is that you take your bits, you block them, and then you encode them, each block.
Can you say one more time how you got that the Golay codes can detect 7 errors?
So it's 8 minus 1. So that's sort of a general insight that I sort of maybe swept under the carpet as I was speaking, that if the minimum distance is 8, then you can detect 7. And the reason is that if you really were to change 8, you might now go from one good code word to another good code word. And then we cannot detect anymore. So 7 would take you almost to the other code word, but not quite there. So you can still detect.
So we have the 99.97% quantum bit, and we have our error correction codes. What's left? What's limiting us from just using those two things together?
So what's limiting us is that once the quantum circuits get pretty big, then even if we start out with some pretty small probabilities of error, then they get I was just about to say they add up. They kind of multiply up, and so the errors just get worse and worse. And if we want to do really realistically sized circuits that could do something like run Shor's algorithm on factoring numbers that are described by, say, 2048 bits, then we need lots and lots of gates, and then we need lots and lots of qubits. And if all of that, even if every single one has a little error rate, it all goes bad once you have many of them.
Is there a name for the 743 code?
I don't know the name, but in some sense, that's the beauty of this field, is that we can just call it the 743 code. Then we know all we want to know about it. Okay, I have 9 minutes left. I want to say something here about at the end about the following question. Okay, so we have linear codes for all kind of classical stuff: computers, storage, communication, and then we want to do this transition of saying, let's just take all this classical, let's call it linear codes. So now we've restricted ourselves to that, and then we want to move this over to quantum. What is that easy? Is it hard? And I'm going to make the case here that whatever it is you're going to hear from Ken Brown tomorrow is actually brilliant. And it's brilliant because it overcomes 3 challenges that each of them seems to just be insurmountable when looking at it at first. It really just looks like that this thing here, this arrow here, just ought to be impossible. And so here are my case. So I'm going to make the case that this just seems impossible. So the first part of the case is that when we go to quantum, we have the no cloning theorem. And the no cloning theorem is saying that you cannot just go around and copy an unknown qubit. That's just prevented by quantum mechanics. And so if we cannot copy a qubit, then how on earth are we going to do anything like this that I've been talking about all the time? Oh, I'm just going to duplicate a 0 to 3 zeros. If we cannot clone, this thing here just seems to be not possible. Well, so no cloning theorem says we cannot clone an arbitrary qubit. And of course, here we're not really starting with an arbitrary qubit. We're starting with 0. But of course, we also need to clone 1 to 1, 1, 1. So how on earth are we going to overcome this? If what I've been saying today is that this case over here is like the base, and then everything else is just trying to be smarter than that, still using linear functions. So if we cannot clone, how are we going to do that? So it looks like already point number 1 just sinks the ship. It's just like not possible. But it doesn't stop there. The second challenge is that when we look at a qubit, so what is a qubit actually? So a qubit is clearly not 0, 1. A qubit is something like alpha beta. And we know that these alpha betas here are complex numbers. They are not bits. They're way more complex numbers than they are bits. And so it means this whole idea of saying, well, we can have a bit flip, and that's all we have. 0 flips to 1, 1 flips to 0. It's like, yes, but in quantum computing, it's not a bit flip. It's like alpha can flip to any other complex number. Beta can flip to any other complex number. How on earth are you going to control this? If it's already a lot of trouble to think about just bit flips, then how are we going to do anything for complex numbers? There's like way too many of them. Not to mention computers are finite things. Even quantum computers are finite things. How are we going to deal with one complex number changing into another complex number? So again, I would claim that if you just think about this for a moment, it looks like this whole idea of moving linear code to quantum just looks like utterly impossible. But it still doesn't stop there, because there's a third thing about quantum, which is that measurement destroys any kind of superposition that we have. And we know that a lot of the power of quantum computing comes from being able to put our quantum states into superposition. And so, so you can imagine we're computing, and then at some point we want to correct an error. How do we correct an error? Well, the first thing we want to do is we want to, with linear codes, we want to apply a parity check matrix. What does the parity check matrix do? Well, it essentially does some kind of measurement. And we find out, we do some measurement, we find out what the bits are in this corrupted code word in front of us. We do some math on it. We come out with an error syndrome, and then we make some decisions based on that. But in quantum computing, we cannot just go around and measure stuff, because we're going to destroy the superposition that is the state. So this whole idea of applying a parity matrix just seems completely dead on arrival. We cannot do that. It just doesn't work. We no longer have our quantum state at that point. So again, I'm going to make the case that if we just think about this third point for a moment, it looks like the idea of taking all this linear code stuff and moving over to quantum is just utterly impossible. And then if you combine all of these 3 reasons, then it just looks like there's no reason to show up tomorrow, because there's just no way Ken Brown is going to pull this off. And so what the good news is that the entire field of quantum error correction, what it does is that it actually solves all of these 3 problems and makes it work. And so that is the final message for you here, is that quantum error correction solves all these 3 problems. It cannot undo the no cloning theorem. It cannot undo that qubits are made of complex numbers, and it of course has to do measurement. But what it does is that it sidesteps all of these problems in a way so that we can still do quantum error correction. And with that as the motivation, Ken Brown tomorrow will show you how to do it, and I can assure you that it's brilliant. So what I will do today is that I have lecture notes. I have 12 pages of lecture notes that give some notes on what I was talking about today. And what I recommend you to do is, what we will do is that after the lecture here, I'm going to get them posted on the webpage for the spring school, and then just take a look at them tonight before, or tomorrow morning before Ken Brown starts to talk, and you will be completely ready for quantum error correction. Any final questions?
Are there any theorems on the bounds of n and d with respect to k from before?
That's a very good question. I don't know such theorems, but they're probably there. In a way, I think I know such theorems, but I just don't remember them right now. So yes, so there are some theorems that talk about how much you can squeeze out of error correction, and I wish I could quote them now, but I don't remember them.
Only arbitrary or unknown qubit states cannot be copied. But if the state to be sent is prepared into a well-known state, why couldn't it be copied?
Then that's exactly the kind of thinking that the quantum error correction people get into, that they find ways to be in a known state exactly when you need it. And that's taking the first step towards quantum error correction.
When and where can we find the video of the lecture once it's posted?
Oh, that's a question for the organizers. I think that they will post the video, but things take time, so don't expect it to come too soon. But the lecture notes will be up today.
And I'll just add that the plan is to have the videos available both on the website that you use to access this, and then ultimately our institute's YouTube channel. So probably 2 weeks until that happens.
Very nice. Other question?
There was a question from before, which was how to determine the maximum Hamming distance. I don't exactly remember the context for that. But
so yeah, well, so the maximum Hamming distance, I think that would just be hard work. I don't know of a quick formula that does that. Minimum Hamming distance, that's the thing I talked about. I think that the maximum Hamming distance is less interesting than the minimum Hamming distance, though.
How necessary is the field of classical error correction theory to the relatively newer field of quantum error correction theory?
The way I see it is that when I read quantum error correction papers, I have so far always been able to draw a straight line back to ideas in classical error correction. And so it begins with this whole idea of linear codes. And then you can take something like, for example, these repetition codes. There will be something there in quantum error correction that picks up on that. You can take Reed-Muller codes. There will be something in quantum error correction that picks up on that. And you can sort of go down the line. Whenever there was an idea for linear codes in classical error correction, somebody has been working on it almost always in quantum error correction. So I think the basic point here is that the classical guys have like 50 years of head start on it, and then the quantum guys are just like picking up on whatever ideas they can find. But then, of course, the quantum people need to do more because they have this whole list of trouble on this slide here. So they all add new ideas to get stuff done.
How would you determine the biggest minimum Hamming distance of a code set?
So I do not understand what the biggest minimum distance means. I need more context or more explanation to understand this.
So please resubmit your question with a little bit more context. Do you think there's anything in quantum error correction that classical error correction can borrow for its betterment?
Not that I know, but it is true that in some sense the quantum error correction is a field that's trying to do more with less. So they're trying to do more because they have to correct errors on complex numbers, and they're doing it with less because they can only do it with unitary operations. Or if they can somehow bring in a classical computer to help do something. So it's quite possible that this thing of doing more with less can inspire the classical people. And I think that this has been a general theme in quantum computing, that there's a whole field out there of quantum machine learning And the quantum machine learning people have developed tons of ideas. And then the classical algorithms people are looking at that and saying, oh, we can borrow some of those ideas. And that actually made the field of classical machine learning better. And I could imagine the same would happen for error correction.
Is the 743 code the most data efficient linear code known?
I don't think so, but it's definitely a good one. And so I must say that you should ask that question tomorrow. Because I know that Ken Brown plans to talk about the 743 code, and he will do that for a reason, because he thinks it's good. And so just ask him, do you know of anything even better that is a good one?
Here's a follow-up on that previous minimum maximum question. For a 24-12-8 code, can we make the minimum Hamming distance bigger, say 24-12-10?
I don't think that is known. So I think this is related to the question earlier about, is there some kind of limit theorem on what we can do with an n and a k and a distance? And I think that 24-12-10, I think, is more than we can do. I think that's asking for too much. But it would be good to have the theorem in front of us to be able to do a little bit of math on it. I don't, when the numbers are 24 and 12, I don't know anything that does better than 8 over there in the third position.
All right, I think that's all the questions.
Very good. Okay, thank you everybody. This has been great. Let me just say that the organizers have set up a gather town starting at 12:30 Pacific time, so that's in 25 minutes. And you can go to the schedule and find the link. And today is like a social day. The idea is go there, wander around. There will be tables, sit down and talk. The whole point is that starting tomorrow, Gather will be used for discussions and working through problems. There will be exercises. There are no exercises today, but there will be tomorrow. And so it means that Gather will be the place for working on that and talking to other people about the exercises. So today what we should do is take a break for 25 minutes and then go over to Gather and then talk and just get familiar with how this Gather works for this summer school, for this spring school. And then we'll be totally ready we will both know each other better, and we will be ready for tomorrow. So let me just say for myself that this was a pleasure. Many thanks for all the good questions. It was delightful to have this morning together, and see you all tomorrow for Ken Brown's talk and Gather in 25 minutes.